Yep, recording is on. Something was happening in the chat room, I can see. What's step 4? Oh, guys, what did I miss? Turtle. Just do we HV access to red center like math? Do we have access, I guess, right? Yes, I think yes. I think the red center is now fully open. Yeah. Why? E hats red center. What's the red center? That's the building where math department is. Yeah, on campus. All right, things are being recorded. We can continue. So I said I'd like to entertain you with the proof of Schwartz of Cauchy-Schwartz, and it's a beautiful proof, and it's so simple. It's surprising that such a great inequality has such a simple proof. But all great things are simple, right? Some people say. And I will use this chance in order to do one extra thing. I will try to summarize some properties of a dot product which are key to the proof of Cauchy-Schwartz. Because later on, we will try to briefly, we will have a brief time when we'll try to extend this to other vector spaces, because I said everything we do right now is very specific to n tuples of reals, but we'll do it to the other vector spaces as well. And the properties of a dot product I'm about to summarize, they will be useful. We will make them into axioms later. The first thing about the dot product, which is very evident in the formula, the way it's defined, is just it's commutative, right? If you change the order of factors, nothing changes. It's the first property I'd like to keep in mind, commutativity of a dot product. The second one is a linearity. Oh, just give me a second, I need to close this. The second one is a linearity. It's called linearity with respect to the first argument, right? I mean, I put the linear combination into the first factor of my dot product, and I can break it into linear combination of vectors individually, right? Linearity with respect to the first factor. Thanks to commutativity, we have also linearity with respect to the second factor. It's sort of like a corollary of the first two properties. That's the second property I'd like to have. They're all evident from the actual formula which defines the dot product. The third property, it's not difficult, but it probably will be a new thing. So I hope you remember it. If you do a dot product of the vector with itself, it's a non-negative value. It's again evident from the formula for a dot product. Like that's the reason we could take a square root and ended up with a non-negative value for a length. Also, at the same time, if it happens that the dot product of a vector with itself is 0, the vector itself is 0. It's because when you have a sum of squares and it equals 0, and they are real numbers, that's why it doesn't work for complex numbers, by the way. That's the reason why I can't do the dot product for. I can write the formula, but these properties won't hold, and that's why, for instance, you won't have proof of Cauchy-Schwartz for complex numbers. But for reals, if you got sum of squares, which is exactly 0, which it means every term is 0, and hence the vector is 0. These two together, they have a name, like this has a name, commutativity. This has a name, linearity with respect to the first factor. These two together, they've got a name which you have to remember. It's a very known name. It's called the positive definiteness. Positive definiteness. And in plain English, you can summarize like this: dot product with itself is non-negative. Dot product with itself is 0 only for 0 vector. That's the summary of this symbolic writing of positive definiteness. These are the properties of a dot product, which are evident from the formula, but these are the properties themselves which are needed for the proof. Later on, when we try to extend it to other vector spaces like complex numbers, again, tuples of complex numbers, we will take these properties and we convert them into requirements onto something we're going to use instead of dot product. These three axioms: commutativity, linearity, positive definiteness. There will be requirements as axioms. Right now, they're just evident from the formula of a dot product. Right. Now, it's based only on these properties, yes. And everything else we're about to do, the angle, the length, and the other two concepts, they're all based on just on these three properties. That's why once we come up with, once I offer you a replacement of a dot product in the other vector, in the other primary vector spaces, which are subject to these requirements, axioms, everything else will follow. Right, proof. Yeah, that's how it goes. It's very simple proof. You see, I don't need much space. The entire proof will fit into the quarter of my screen. My first observation is if I can consider this interesting vector, x plus ty, x and y are n tuples, t is just a number, right? That's the linear combination of two vectors. And I take the length squared, which means dot product with itself. It's a non-negative thing. That's the positive definiteness, right? Yeah, that's due to positive definiteness. We've got this conclusion. That's my first step. My second step, I will expand this. Thanks to this linearity and commutativity, I can basically expand the brackets like with numbers. That's my expansion. X dot product with x, y dot product with y, and t square, and the mixed factors x with y and y with x. It's 2x plus y, x dot y. That's my expansion. And because this equals to originally to this expression, I can claim that this is non-negative. Okay. Now I'm going to analyze this expression now from with respect to t. With respect to t, this is a quadratic expression, right? Very simple, very numerical quadratic expression like this. Yeah. It's a quadratic expression like this with coefficients a, b, c. A, c being x dot x, b being double x dot y, and a being y dot y. But if you just name this with a, b, c, that becomes very known, very familiar quadratic expression. And what we know about this quadratic expression, it's non-negative for every t, right? Because it comes originally came from here, from positive definiteness. This happens for inequality. It's a high school stuff, how we solve quadratic inequalities, right? It happens when the corresponding equation has at most one solution, or in the geometrical terms, when the parabola, the parabola graph of this function, either above the axis or exactly, the vertex of that parabola exactly on the axis. That's the only chance for this inequality to be true for every t. If your parabola is below the axis, you'll have two intersections, then there will be negative part. And in terms of coefficients, so this equation has either none or one solution. This quadratic equation with respect to t has either one or none or one solution. That's the only chance for this to be true for every t. This is a high school stuff we're applying right now. The only extra thing is that my coefficients are originally linked to my vectors x and y. But if you forget about this, if you think of them as just numbers, this piece, absolutely high school stuff. So for the quadratic equation to have this outcome, we know how to test for that, right? There is a condition on coefficients which guarantee or which is equivalent to this outcome. None of the solutions or one solution. It's called we compute this thing which is called discriminant, like this, b squared take 4ac, and it's supposed to be non-positive for this to happen. That's how we actually analyze quadratic equations. We compute the discriminant, and if it's positive, we've got two solutions. If it's zero, it's one solution. If it's negative, no solutions in real numbers. No complex right now. And now time has come to remember that my A, B, and C were originally linked to my vectors, right? I'm going to put it back here in this inequality. Yeah. That's how it will look if I put back my A, B, and C in terms of my vectors. And that's exactly Cauchy-Schwartz. I mean, if I take the square root, if I cancel 2, and if I remember the dot product of the vector with itself is the magnitude, if I remember all of this is exactly the Cauchy-Schwartz inequality. How beautiful it is. Who would have thought that such a great inequality, which is the most important inequality in the entire of mathematics, is linked to such a simple fact from the high school about the quadratic equations. It's quite amazing, I'd say. Okie dokie. Let's move on. Yeah, we're doing great, and I'm recording. Yeah, that's right. So now we have to discuss with you two other concepts. So we discussed with you angle. I mean, magnitude, length, and angle. And now we're going to take it to other concepts. They are way harder. And first, I will just demonstrate them, mostly demonstrate them on two-dimensional and three-dimensional examples. After we get some understanding of that, I'll present you these concepts in general. We're still in the concept in the context of Rn and tuples of real numbers, but now we're going to narrow our setting even further. We're going to look at the couples only. Not just before angle and length, we did this for the n tuples of real numbers. Now we're going to do things for couples of real numbers, two-dimensional case. That's how difficult those concepts are. They require a lot of geometry, a lot of insight, but we're going to take it back to the general Rn after we relatively confident with the dimension 2 and 3. So orthogonal complement and two concepts. You have to remember the name in the first place. Orthogonal complements and orthogonal projections. But when you say projections, often orthogonal people drop this. I mean, there are non-orthogonal projections, but we're not going to meet them in this course. So you can safely forget that. And I will often just say projections rather than orthogonal projections. But official name, orthogonal projection. So I'm going to use this picture to demonstrate what's happening. So on this picture, you've got two perpendicular lines, this black line, and a couple of vectors, blue vectors, orange vectors, and the pink one. I will name them as we go, and I will show you, I will use them to demonstrate these concepts, orthogonal complements and orthogonal projections. That's my 2D plane. That's the R2 case. Right. So two black lines. In the language of vector spaces, these are subspaces of my R2. Right? These are subspaces of R2. So if all right, what's happening? Yeah. If I call these two blue vectors somehow I don't. I know what's happening. Sorry. I think I know what's happening. Yeah, that's right. Yeah. So we'll just go back a few steps. So two black lines, they are subspaces. This is a black line, which I'm going to call subspace U. This is a black line I'm going to call subspace W. Okay, they are one-dimensional. They span by blue vectors. I'm going to call them B1 and B2. This is a vector B1. This blue one will be B2. So my subspaces U and W, they span by B1 and by B2. Both of them are subspaces in R2. This is a subspace in R2, and this is a subspace in R2. Yeah. All right. So I'm using this graph, and I present the analytical symbolic writings for the elements of this graph. It's very, very useful to keep this picture every time you think of orthogonal complements and orthogonal projections. Every time, 3D picture, which will be more diverse. So on my graph, you can see that I intentionally made my vectors perpendicular, and that's important. So orthogonal is we do things orthogonally right now. Perpendicular means the angle between is 0, or in the language of dot product, it means, sorry, the cosine of the angle is 0. Angle is 90 degrees. Cosine of 90 degrees is 0. And dot product of those between those two vectors is 0. This is my assumption. Okay, perpendicular vectors. Right. B1 and B2 are perpendicular. Now, here's the language. The subspace U by itself is just a subspace which is spanned by one vector. But if you think of the subspace U in relation to the subspace W, because they are two perpendicular, these are two perpendicular lines, U is what we call orthogonal complement of W. And vice versa. If you think of a W in terms of U in relation to U, I should say, W is what we call, it's just a name, not definition yet. W will be orthogonal complement of U. Okay, the subspace U in relation to W is called the orthogonal complement of W, correct? Similarly, the subspace W in relation to U is called the orthogonal complement of U. So the idea of orthogonal complement assumes sort of two subspaces, which are, well, in the current demo, one-dimensional and spanned by perpendicular vectors in 2D space. Everything right now in 2D. Symbolically, we write this. That's how we write these sentences in symbols. We use this perp symbol as a superscript. So this one says W, orthogonal complement of U. That's how you read this identity. And this one reads U is the orthogonal complement of W. Yes, symbol, when I write this in text, I will write U perpendicular. Symbol U perp stands for the orthogonal complement of U, and symbol U W perp stands for the orthogonal complement of W. These are just the names. Now let's just try to formalize this as a definitions. They're not the most general definitions because we're in a 2D case, but that will give you some ideas. These are just the symbols. The formal definition of orthogonal complement, that's how it stands. The orthogonal complement of U, listen to this, all those vectors on the entire plane which are perpendicular to every element in U. Here's my U. That's a straight line. If you try to imagine all of the vectors on the plane, all possible vectors, just imagine all of the plethora of vectors here, but you only pick up those which are perpendicular to everything on U, you will end up with W. And that's exactly what the orthogonal complement is. And that's how we define it. All those vectors on the plane which are perpendicular to everything in U. It's a rather complex definition because you have to check this perpendicularity with everything in U. It's not practical to check it using this definition. There are many things which are practical to do with this definition, but not checking that something is orthogonal complement. For checking, knowing that U comes with the basis, way more useful, because if you know U comes with the one-dimensional and one-element basis, you can simplify this longer definition into a simpler equivalent thing. Well, first I just say this writing in plain English. U perp is the set of all vectors in R2 that are perpendicular to every vector in U. That's what this definition reads. Now, thanks that we know the basis in U, one-dimensional, since in our demo, U is one-dimensional, U perp can be described simpler, thanks to the fact it's one-dimensional. Yeah, that's how we can describe it. U perpendicular, all those vectors in R2 which are perpendicular not to everything in U, but just to one vector in U, that particular single basis vector. See how simple it became? And this is in terms of finding U perpendicular in your tutorials, this will be way better than the original definition. And you will see this in the examples next week on your tutorials. Okay. I can say the same about W. I don't think I did on this slide. No, I don't have space. But you can safely replace U here with W here. So U here with W and U here with W. And that will be the definition of the W perpendicular. And again, you replace U with the W here. And the basis B1 with the basis B2. And that will be formula for the W perpendicular in terms of basis of W. I don't have it on the slide. It's the same to use. Yeah, this is important observation. We can describe U prop using basis of U only. Yeah, it's important observation because it will allow you to do, at the very least, it will allow you to do some questions in the tutorial. This is computationally, this is not what we use. I mean, this is useful for other things, more advanced, but for simple tasks, it's relatively simple tasks of finding U perpendicular. Using a basis vector for that is the way to go. Okay, so the next is a projections. Let's just demonstrate what projections are on this graph again. So projections, orthogonal projections. I'm going to name vectors again. My pink vector, I will call it X here. And these orange vectors, which I obtain by dropping perpendicular lines from the tip of the X to my subspaces U and W, marking the intersection and stretching the vector all the way to that position. The orange ones, I will call them O1 and O2. O for orange, obviously. B for blue, by the way. That's how I chose the names for my vectors. Right. I'm going to call them O1 and O2, and I'm going to use them to demonstrate the idea of projections. Naming-wise, vector O1 is the orthogonal projection of the vector X onto the subspace U, right? That's my orthogonal projection. I drop the perpendicular, I end up with the base of that perpendicular, the vector in the U. That's the orthogonal projection of X onto U. For the same reason, O2 is the orthogonal projection of the same X to W. Right. Symbolically, we write this like this. This is a notation we're going to fix. P with the sub-index being the name of a subspace, this symbol, especially in chapter 4, absolutely no exception. It will stand for the orthogonal projection onto subspace U. Orthogonal projection onto subspace W. 1, U2. That's what we write symbolically for this longer paragraph. U and W are one-dimensional, and that's, again, it's a great help that they are one-dimensional for projections, as much as it is very similar to what happened here. U and W are one-dimensional, so the projection is called one-dimensional projection. Yeah. One-dimensional projections are easiest to study, that's right. We will need to study projections on high dimensions, we'll get to this. But for one-dimensional, they are the easiest of all, and one of the advantages of one-dimensional projections, we've got the direct formula how to compute them. We don't have this privilege for higher dimension projections, but for one-dimensional, there is such a direct path. Here it is. One-dimensional projections can be computed directly using basis vector, the basis of the underlying subspace. For U, it's B1, for W, it's B2, right? And that's how we do this. That's how we use. Yeah, that's my way to compute this. So first, I will show you actually the derivation of that formula. So if I aim to find O1, this vector, and I aim to link it to the basis of my subspace, which is B1, first I rescale, right? Look what I've done. I took vector B1, I divided that vector by the length of that vector. You see magnitude with inverse, and then I multiply by the length of O1. This is just in the geometrical terms. When you multiply a vector by a scalar, you scale that vector lengthwise, make it shorter or longer, depending what you multiply with. So this is the rescaling. The step is based on the rescaling, right? I just, as a side comment, I point out that if you take only this component here, if you take a vector, in fact, it works for any vector. If you take a vector and divide that vector by the length of that vector, what you end up with is a unital vector. It's a very powerful technique to end up with the unital vector. So the vector U the length of that vector is u. Okay, so the magnitude of u is 1. Let me just make it part of this. Part of this slide, this statement for the future, like this. It's just a side remark. We're going to do this often. Actually, we're going to divide vectors by their lengths a lot very soon, because we will soon learn that having unital vectors is a very good thing, as opposed to non-unital vectors. I mean, a very good thing computationally. So we're gonna literally hunt for those vectors with the length 1, and that's the way, and some other properties as well, actually, to be honest. And that's how you can convert any vector to a unital in the same direction as v1. Right, so I continue. We remember I was trying to derive a formula for one-dimensional projection. So my first step, it's a rescaling. First, I take my v1, took a unital, and scale that to O1. That will be O1. My next step will be trigonometry. My next step is a trigonometry. Yeah. So I'm saying that this O1, which is the length of this vector, if I use high school trigonometry, I can alternatively compute this length by taking the length of the x vector in this right angle triangle and multiply by the cosine of this angle here. That's a high school trigonometry. I replace my length of O1 with the length of x and a cosine of the angle in between. Okay, that's a trigonometry from the high school. It's a geometry involved here really heavily. Now, my next step will be for the cosine. We've got a formula from the slide before, the one which computes the cosine, and now we can rely on that formula after Cauchy-Schwartz. That's the formula from the slide before. That's how we compute cosine between two angles, x and b1. And now we can do quite a few cancellations. X cancels with this x, and this b1 inverse, and this b1 makes it square. And that's how we arrive cosine through dot product. Yes, that's the step here. I replace cosine through dot product. So once I do cancellations, that will be the formula for the one-dimensional projection. It's a very powerful formula, and you need to remember that. And I think you saw this formula already, and probably in derivation of that formula in your first year algebra as well. So, yeah. Formula for one-dimensional projection in terms of the basis, right? Yes, in terms of the basis vector of the underlying subspace. Yeah, that's projection onto the subspace U of X computes like this, or you can even say like that: projection onto the subspace spanned by, it's a typo, not U, it's supposed to say B1, spanned by the vector B1 computes like this. I think in your first year, you use the notation like this. You rather than saying the subspace in a subscript, you just set the vector on which you project. I think the notation which was used in the first year book is like this: projection onto the vector B1. That was acceptable because in your first year algebra, you only did one-dimensional projection. So the only thing which mattered was the vector itself. In this course, we will do projections on subspaces, not only 1, but 2, 3, and higher dimensions. And that's why we need to use notation in full rather than the vector itself. We put actual subspace into the subscript, either U or span. Okay, that's if you remember this from the first year. Right. Okay, let's continue. Well, similarly for W, there will be a similar formula, but this time I will need to use the basis vector for W, which is B2. Yeah, right. From the geometry, I need to, that's right, yes. Okay. The last comment which I will make about this geometrical, so far, we've made a few really fundamental observations. The first of them will be the definition of the orthogonal complement. and what it means geometrically, orthogonal complement. The second one is how the orthogonal complement can be found through the basis. It's a very fundamental to what you need to do later. Third fundamental one is the formula. Am I online? Okay, do you hear me? Another confirmation, please. Great. Okay, okie dokie, no problem. Thank you. I think because I'm sitting on a wired connection. I made a wired connection to this room to have faster. But I think I just touched the cable in the cable. Oh, actually, probably I don't know. No, probably not that. Never mind. We're good. I think we're good. Recording. Where's my screen is not. I'm not sharing my screen, right? Yes, the screen goes back up. And I think the recording is still going. Yes, I think I see the sign. Just double check. Yes, the recording is still going, so I think we're all good. Yeah, Zoom is actually way more stable. Thank you guys for staying with me for the first 2 weeks of experimenting. I was planning. Yeah, I think my wired connection is good. Anyway, so where did I stop? Did you? So I think this was this part, the similar formula for W. It was, I think, was part of the. I think was good. Okay, so again, I was trying. Yeah, I see where I stopped. I was trying to summarize the important things which was part of this slide. So first one was the definition of orthogonal projection. Sorry, scratch that. Or orthogonal complement. Second is how we can find orthogonal complement using the basis vector. Formula for one-dimensional projections. Yeah, it's either these things, they either come from my demo or from actual careful analysis like this one. Now, another fundamental thing which will be part of this slide, it's about to come, it will come again from this. And what I can see from the geometry on this slide is that my vector x, I can actually I can reproduce that vector by adding these two projections, O1 and O2, right? It's that parallelogram rule which I mentioned today. In this case, parallelogram will be a rectangle because these two lines are perpendicular, right? So if I go back to the language of projections, it means that any vector x, this x vector was absolutely random, breaks into a sum of projections onto a subspace, and listen carefully, and that subspace orthogonal complement, right? That's one of the fundamental connections between orthogonal complements and projections. See, vector x breaks into sum of projections onto a subspace and orthogonal complement of that subspace. And that works for U and W identically. You can write the same thing for W. That's another very fundamental fact which will be present even in a very generality when we take it to any dimension. But right now you see the demo of that fact on this plain example. Yeah. So if I can actually write this now using the language of linear maps, I can say, rather than using the x, I can say the identity map breaks into a sum of two projection maps. Projection onto a subspace and projection onto that subspace orthogonal complement, and the same for W. And I said linear because projection map is a linear map. It's actually a difficult fact, which, I mean, you need to test. Remember how we check that everything is linear map. We got this 1 + 2 on 1 or 2 properties, linearities. For one-dimensional projections, this follows from the formula. I mean, this I stands for identity map, the map which takes a vector to itself. Not identity matrix, identity map. We call projections linear maps because they are linear maps. For one-dimensional projections, this is visible from the formula here, from this formula and from the properties of a dot product. For projections, we're about to meet soon. For the projections not on higher dimensional subspaces, this is still true. They are linear maps, but we're not going to have a proof. I mean, like I'm not sure if I'll have a proof for you. That will be a challenging proof actually. So I will probably expect you to take this as a fact without a proof. But projections are linear maps in general, and for one dimensions, that's just visible on the formula. Right. I think that's the end of the one-dimensional demo or two-dimensional demo. And what will happen next? I will repeat all of this in 3 dimensions. Okay, it will be very similar in structure, very similar in names and concepts, but there will be extra complexity. If you got any questions about what you see right now, see, I packed a lot on this screen, but it's good that I can pack so much in one screen so you can actually see everything at once. It's great. I like this. I like when I see everything at once. That's why I like blackboards. You can put everything at once and you can analyze that. That's why I hate the PowerPoints, because you can't put everything at once in a PowerPoint. And for math presentation, that's extremely important to have everything at once in front of you. So you can, with your eyes and in your brain, you can link things together. If you got anything to ask, go ahead. It's a very challenging topic. Don't be surprised if you don't have questions. You will have questions, and we'll discuss. It's not part of the upcoming test, so you don't stress about this yet, but it will be part of a test eventually. Test number 2. I'll give you a couple of minutes to think, and then I'll move on to the next slide. And may I please just double check once again with you that everything is good connection wise. Just give me something. You hear me well? You see everything okay? Nothing is freezing. I'll just do a chat room. Oh, something in the chat room again came up. Okay, good, all good. 143. Yes, thank you. Okay, let's move on. So now I'll do, like I said, everything in 3 dimensions. And we will do everything in general on Monday probably. So that will be my graph this time. So 3D, I hope it gives you an impression of 3D. I try to use the same coloring for the vectors. I mean, the vectors colored with the same colors to the 2D picture, they will play the same role. Right. So the plane, this time the subspace W will be a plane. Yes, so this W stands for this halo-looking, I guess the geometrical name of the quadrilateral, which represents the plane, some plane, and the U will be this black line. That's the subspace U. So already we have a difference. W is 2-dimensional, and U is 1-dimensional. That as much I can fit in 3 dimensions. Right? The blue vectors. This time we've got 3 blue vectors. B1 down here, which is in the plane W, B2 down here, which is in the plane W, and B3. Where's my B3? I don't know what happened to B3. It's probably next step here. B3 is this blue vector down here, up here, sorry, and that's the one which is in the U subspace. Okay. So my W is spanned by 2 vectors, by 2 elements. So base will be of 2 elements, B1 and B2, right here. And my U still spanned by 1 vector, B3. That's the picture you have to, and that's it's a more complex picture. You have to keep this picture in mind every time you do anything with orthogonal complements or orthogonal projections. That's the best guiding principle, which is, which encodes everything. Right, we again work under the assumption my plane W perpendicular to my line. This line is perpendicular to this entire plane. In a vector language, it means that the basis of U perpendicular to basis of W. There's no any perpendicularity between these two. They may be not perpendicular. It's irrelevant to what we do. Okay, so yeah, so I will probably say this explicitly. B1, sorry, what's that? B1 dot B2 not equals 0 in general. It may be not. It's irrelevant to what we do, okay, in general. I'll do it probably here. I just realized I got lots of space here only in general, meaning that sometimes it may be, sometimes it may not be. If it is, that's a great help actually. If the B1 and B2 are perpendicular, that will be a great help, and we will be hunting for such bases for the subspaces soon. But for what we're about to do, it's irrelevant. That's why in general it may not be 0. Right, the space W is now I repeat the same language, which is good. I mean, repetition is always good when you do new things. The space W in itself, it's a space with dimension 2, with the base B1, B2. But in relation to U, it's orthogonal complement of U, because this line perpendicular to this plane. The same applies to in reverse. The space subspace U by itself, one-dimensional subspace, nothing interesting about it. But in relation to W, it's orthogonal complement of W. Okay, symbolically, that's what you write. Symbols do not change. Now, I just repeat the definition, which actually absolutely the same this time. W perpendicular, it's all vectors, but in R3 now, not R2, which are perpendicular to everything in W. Okay, and that will be this line. All the vectors, all the plethora of vectors in R3 which perpendicular to this plane, they will make up this line, sorry. And in reverse, this time it's a bit different. Well, the definition is not different, it's the same, but the outcome is different. U perpendicular, again, all vectors in R3 which are perpendicular to everything in U, right? If you take all of the vectors in R3 which are perpendicular to this line, you will end up with this plane. Yeah. Right. Again, finding these two things, finding the orthogonal complement is done. This definition is, yeah, you can safely say it's useless for finding things. It's very useful for other things, higher things, analytical thinking, proofs. But for finding, using bases is a way better. These bases, but this time it will look different because W has two elements in a basis. So this time there will be two identities we have to check. W perpendicular, all vectors in R3 which are at the same time perpendicular to B1 to every element of the basis of W. For U, because U is one-dimensional, it's no different to two-dimensional example. All vectors in R3 perpendicular to the basis of U, one element there. Projections. I'll just see. So this is an important fact, which is this is important fact, which will help you to find orthogonal complement next week in tutorials. Projections. I will name things again. My pink vector X, dark pink, and we've got two projections. One of them we draw perpendicular onto the plane. There's a base of that perpendicular and the orange vector, which stretches to that base, O1. And now we draw perpendicular onto this line, U. There's a base and the vector stretches. That's the, I think, O2, I call this. Yes, two vectors, O1 and O2. These are my projections. Okay. Vector O1 is the orthogonal, it's a naming, projection of vector X onto the subspace W. Vector O2 is the projection onto the subspace U. U is one-dimensional, so here again, we can benefit from that great formula. Projection onto one-dimensional subspace is given by the formula like through the basis of U, which is actually B3, not B2, it's a typo. The basis of U on my graph is U3, so this is supposed to be, I need to change this to B3 everywhere. Yeah, here it is, direct formula. Now, projection onto W, this vector, that's the way harder to find. We don't have a formula for that. We don't have a formula. We have a method rather than a formula, and that's a method we're going to learn soon. That's why actually this condition will be critical, because if this condition is not met, I said it's irrelevant for what we do, and it is. But for that method, which finds projections on W, this condition will be critical. It will be a difference between easy method and difficult method. If this condition is zero, being zero is met, the method will be almost nearly as a formula. But if it's not met, the method will be way longer. And that's why we'll like this condition so much for the projections. But we'll see this. For now, it's irrelevant. Right, but what we can do, and that's very specific nature of, it's sometimes not specific nature of dimension 3, but sometimes there is a third shortcut. It's not a formula, but it's a bit easier than the general method. And here it is. It's based on this observation again. Some help can be found in the indirect method. Here's this method, which again, important to remember. We use the same fact, right? This vector x can be represented as a sum of two projections, O1 and O2, which means that so this relation which we had before still stands. Every vector identity breaks into sum of the projections onto U and its orthogonal complement, or projection onto W and projection onto W orthogonal complement. This still stands, even though this time W is two-dimensional, and it will stand in any dimension. That's a very powerful relation, extremely powerful relation, this one, between projections and orthogonal complements. And this is the one which will allow me to find projection on W easier, because what I can do, rather than finding W projection on W directly, I can solve this for O1 here. If I solve this for O1, here, I can say this. And so rather than finding projection directly onto W, I can project onto one-dimensional one, for which I've got a very nice formula, and then do subtraction. This is the indirect method, which sometimes helps. Because like I said, this direct method in general, it's a difficult method. We'll get to this. Oh, yes, Julia, please go ahead.
Sorry, is that supposed to be O1 equals to X minus O2?
Yes, it's supposed to be exactly that. Thank you, Julia.
Okay, thank you.
Yes, this is my indirect method. Yes. Yeah, and that's in the language of linear maps, the projection onto W equals to identity. So it's supposed to be X here. X minus projection onto W perpendicular, which is one-dimensional. W perpendicular, it's U, it's one-dimensional. Yeah, and this is in the language of linear maps. Projection on W, identity take projection on W perpendicular. Yeah, the trick has only limited use. Yes, it has only limited use, exactly. It's only useful when your W perpendicular, which is U, is one-dimensional. If it's not, then you're not gaining any advantages with this trick. But if it is one-dimensional, if you project onto something to which orthogonal complement is one-dimensional, so you can use direct formula, then this trick has advantages. In other cases, often dimension higher than 3, we need to develop a direct approach to projections, and we will develop that approach. My timing is perfect today. I'm finished. I mean, I finished everything I've got so far on this slide. There will be more. We're gonna look at expanding this to the NEN tuples. We're gonna look at the direct method for the projections. This one, that will be on Monday, and there will be some subsequent concepts. But this is projections, in orthogonal complement, and this method that will be the hardest part of this chapter. I promise you that, and that will be on Monday. Let me know if you got any questions. I'm sure you'll have quite right now. Probably it's too much to expect questions from you, like meaningful questions, because you need to spend some time with this, and you will, I hope. I think we're good today. Thank you very much. I think we can wrap it up. I will stop the recording. Just give me a second. Last time when something just happened and I struggled with that.
I just have a question that another student brought up. Here you say that B1 times B2 is not 0, but in another slide you say that B1 times B2 is 0.
Yes, but in the other slide, in the, let me just help, let's close this, sorry. Oh, sorry, I stopped this screen share. This comes up, it comes up again. In the other slide, I did say so, but in the other slide, am I online? What's happening? I should be. I'm online.
Yeah, you're
right?
online.
And you see everything, right?
Yeah.
Yes. In the other slide, I did say so, but I did say so because in the other slide, B1 was a basis in W and B2 was a basis in U. Okay. So
you've written B2 dot B1 equals 0 just directly above the photo there.
Right. Okay, I see. Yeah, no. All right. Thank you very much. This is a typo. It's supposed to be free. Yes, that's was, if this was confusion, my apologies. Yes, it's supposed to be free. So this, what I'm saying is that the U is perpendicular to W, but there's no perpendicularity within W. This is exactly what happened on this slide above here, because here again U was perpendicular to W.
Yeah, I see. Thank you.
Yeah. Thanks, Mamaka. Thanks for bringing this up. That was a typo, of course. Yes. Thank you. I think we're good to. Did I stop my? Sorry. Did I stop my? I just double checked that I stopped my recording. Now we have a chat here. No problem.
Sorry, sir.
Yes. Just give me a second. I'll stop the recording.